Welcome to this Chemistry World webinar, shining a light on chemistry with in-situ photo NMR. I'm Philip Broadwith, Chemistry World's business editor. So today we're using the GoToWebinar platform. And for those of you who are not familiar, GoToWebinar is an interactive platform, and one of its biggest advantages is that you can ask questions for our speakers at any point during the webinar. That's a really important part of the webinar. It's where we think that you get the most value out of interacting with our experts that we've brought in. So do submit your questions at any point during the webinar. There is a box at the bottom of the GoToWebinar panel, which by default should be on the right-hand side of your screen, but you can move it around if you're a bit more, to help you get a bit more comfortable. Just type in your question, any question you may have, and we'll be able to see those and we can get to them at the end of the session. If you do miss any part of the presentation, or you just want to watch it again, pick up in your own time to pick up the details, any links or resources, we'll be sending everyone a link to the recording in a few days' time. And also to say thank you to everyone who's attended the webinar live. You'll get a certificate of attendance in the same email. So today's webinar is about combining Benchtop NMR, nuclear magnetic resonance spectroscopy, with direct illumination of the samples to study photochemical processes in real time. Light-activated reactions and catalysts, increasingly important in research and industrial chemistry, but using them effectively means that we need to be able to understand exactly how those processes work. That means being able to monitor reactions while they're actually going on is really important, and NMR is a great tool for doing that, getting that kind of structural information. We've worked with Oxford Instruments to bring you information on this topic that we think you'll be interested in from absolute experts in the field. Later on, we'll be hearing from James Sagar, who is a strategic product manager at Oxford Instruments. James is a physicist by training, and he now leads the company's Benchtop NMR applications team. Up first, we'll have Dr. Alexander Golovanov, who is a chemist and structural biologist from the University of Manchester in the UK. He's known as Sasha. Sasha has over 20 years experience in NMR, and his group is now using it to understand and characterize complex biological and chemical systems. But before we go into the presentations, we're going to have the first of 3 polls that will run during today's webinar. So I'll ask Chris to just cue the poll up now. So the first of our polls is, have you or would you like to perform in-situ sample illumination with NMR? You've got 4 options. We do this regularly already. We've done it, but not regularly. We'd like to do it, but we currently don't, or our materials that we work on don't require it. So if you could just put your votes in, and just say, as I said earlier, do get your questions in during the course of the webinar. It really allows us to get organized for the Q&A session and make sure that we get those best questions answered in that session. And just for anyone who might have missed the very start of the session, you will get a link to the recording and your certificate of attendance in an email in a couple of days' time. And if you have any questions at all, whether that's about the content of the webinar or more technical things, then do just drop them into the questions box at the bottom of the panel. Okay, we've got a good proportion of you voted now, so I'm going to ask Chris to close the poll and put the results up. So yeah, I think that's fairly strong vote for. We don't do it at the moment, but we would like to. So I think that's a great audience to have here. This is, something. It's an exciting technique. We wouldn't necessarily expect lots of people to use it already, but that's the reason you're here, to learn about how to do it. So that gives me a great opportunity to introduce Sasha for the first part of the presentation. So I'll ask Sasha to turn on his webcam and make sure that I can hear you.
Yeah, can you hear me?
Yes, we can hear you. Brilliant. And if you'd just like to pop your slides up on the screen. Brilliant. I can see those. Lovely. And I will allow you to take it away in your presentation.
Okay, thank you, Philip, for the kind introduction. So, first of all, thanks organizers for giving us an opportunity to speak about our exciting recent developments. Today I will talk about how convenient and easy it may be actually to use light-coupled NMR spectroscopy in the lab. So light is all around us. It is the source of life itself, but also for us it is fascinating as it drives chemistry and can give us convenient control over matter. The question is, how exactly do we observe and quantify this light affecting the matter? NMR, as we know, is perfect for characterizing the matter. Today I will briefly talk about why light-coupled NMR is important, outline some difficulties in delivering light to NMR samples, introduce our new NMR torch design, and show a few examples of NMR torch applications that were recorded on 500 MHz spectrometer. This will be followed by the second part of the presentation, where James will show some applications of NMR torch for benchtop spectrometer. So, why photo NMR is important? It can monitor light-dependent processes as they happen, judged by NMR spectra acquired during the actual illumination. So it would allow to characterize and optimize photoreactions, check photo-driven switches, nano-devices, and smart materials, and explore photostability of chemicals. This method is orthogonal to optical detection and can be used with many different NMR active nuclei. It doesn't rely on optical measurements and allows using multiple wavelengths all at once with precise control. NMR magnet, however, is a dark place. Whether you use high field superconducting magnet or lower field benchtop magnet, the sample itself is embedded deep inside the machine. Of course, the sample is usually placed from the top, therefore one can shine light also from the top. That would not require modification of the probe head. However, light intensity decreases strongly with distance. So you want your light source as close as possible to the sample. Also, if you shine light from the top, the path length here is very long, typically more than 4 centimeters, meaning significant non-uniformity, especially in light-absorbing samples. You can illuminate from the bottom as well, but the same problem remains with the path length and absorbance, and additionally probe head modification would be needed. Light can be delivered from the sides, but that is impossible without using specialized probes, and then you still need to get around some non-transparent components of the probe heads, such as radio frequency coils. But of course, in this arrangement, the path length will be much shorter. The method that is currently very popular is to use optical fibers, inserting its roughened light scattering end that is stripped of the cladding. It is inserted inside the sample, or this optical fiber is inserted inside a glass insert, which is then inserted inside the sample, thus providing illumination from the inside. The disadvantage is that you insert a foreign material in the NMR active volume, which may degrade spectral quality and may affect shimming or solvent suppression. Also, let's look for a second at the sample cross-section here. Light originates from the fiber in the center and diverges with distance. Even though the path length here is relatively short, the radial distribution of light is not uniform. The irradiance or light flux per unit area may differ around twice or maybe even more between the surface of the fiber here and the inner wall of the tube here, even without any sample absorbance. And this difference may be significant for some chemical systems. Another problem may be coupling of the light source to the optical fiber. Coupling of collimated sources, such as lasers, to the fiber is usually relatively straightforward, but lasers are expensive and complex to work with. And after all, how many different lasers would you need in your lab if your chemical systems require many different wavelengths and the project requirements are changing with time? You can't change the lasers all the time. So recently, LEDs emerged as powerful and convenient source of light. However, LED emitter surfaces are generally large compared with the diameter of the optical fiber, which is usually less than 1 millimeter. And therefore, a lot of light is usually lost in this coupling. And also combining colors or different LEDs into one single thin optical fiber is neither efficient nor easy. So there are problems with using optical fibers. Some do-it-yourself may be needed, for example, stripping or roughening the end of the fiber. There are large losses of light at fiber couplings. It may be difficult to ensure light uniformity. There may be problems with shimming, sample sealing from moisture and air. It may be tricky to use with small benchtop machines, as additional supports for the fibers above the spectrometer may be needed. You can't just bend the optical fiber the way you want, because it will just snap. So setup is all glass and fragile, so high throughput perhaps is problematic. And maybe this is why it is the reason why in-situ photo NMR is not used that widely, although as we see, a lot of people may want to use it. So there are excellent comprehensive reviews on photo NMR that were published very recently, which provide further information about the illumination technology used until now, as well as showing multiple useful applications of light-coupled NMR spectroscopy. So we propose an alternative solution to illuminating NMR samples in situ, which we named NMR torch. As an example shown here, a special 5 mm NMR sample tube holds the sample and at the same time acts as a light guide. LEDs here are positioned directly at the top of NMR torch tube. Light enters the tube through the transparent tube cap and travels within the relatively thick walls of the tube until it reaches the sample area, and there it becomes scattered there around the sample, illuminating it from the outside. And here you see the results of this sample illumination under ambient light, and also fluorescence of the same sample captured through the orange filter. Multiple LEDs can be used here simultaneously, as there is enough space to position several of those very close to the rim of the tube for efficient light coupling. So this is the home-built setup that we have here in Manchester, with 4-channel LED power supply controlled by the NMR power sequence, or you can control it manually as well, and with interchangeable light heads lowered into the magnet by the electrical cable. LEDs inside the light heads are also interchangeable and are cooled by the existing airflow inside the magnet bore or using auxiliary gas supply. As the standard size tubes are used here, this setup, with some perhaps minor variations, can be used on any spectrometer, high field or benchtop, and also without any probe modifications. So you can use potentially your favorite existing probe head, such as cryoprobe, for example, to illuminate the samples inside the spectrometer. Let's look at the cross-section of the NMR torch sample tube. Here the sample itself is located in the middle, surrounded by the thick, transparent glass walls, with light scattering centers positioned on the outside wall of the tube, so they are away from the sample itself. Light is scattered there in all the directions, and at least half of this scattered light gets scattered towards the sample. Some light may be additionally reflected by the components of the probe head that are outside and reflected and scattered back towards the sample. So this provides illumination of the sample from the outside, which is radially uniform, as the square of distance dependence of light from the source is totally removed in this arrangement. So if you get away further from the local source of light, which is this particular scattering center, and you go further closer to another local source of scattered light, so you're never far away from the source of light there. So the typical path length is very short here, only half of the sample diameter, and it is slightly above 1 millimeter. Let's have a look now at some applications of NMR torch for different typical photo NMR tasks. Let's start with the photochemical induced dynamic nuclear polarization, or photokidnip for short. The principles look simple. You just mix a suitable dye with an aromatic molecule in solution, shine light, and enjoy signal enhancement, either positive or negative. This effect is dependent on dye absorbing light, going to triplet state, and interacting with aromatic molecule, with following radical pair recombination being spin state selective, thus leading to hyperpolarization. Importantly, observing this effect requires fairly strong illumination, and traditionally, to obtain strong enhancements, it has been done with lasers. So in this example, we mixed 6-fluorindole, or 6F5 for short, with FMN and illuminated it with our 3-watt blue light head. You can see here spectrum in the dark for this 1 millimolar sample and with illumination, giving rise to around 64-fold negative signal enhancement, which we can quantify using this enhancement factor alpha, where we divide intensity under light conditions by the intensity in the darkness. So we can measure easily the build-up curves, or using the convenience of the setup, can quickly assess multiple samples one after another at different concentrations of 6Fi to determine the optimal concentration that gives us largest enhancement. We can also dim LAD using pulse width modulation to check that the enhancement depends linearly on the light intensity. We can also measure light intensity scattered just outside the sample area using a simple photometer, and we can see that this is also provides very nice linear dependence. So using the gradients in the spectrometer, we can actually image or profile the sample along its length, or z-axis, and that helps us to reveal the actual distribution of light intensity for a number of illustrative examples of various NMR torch tubes. And all of these are kind of relatively bad examples. So the source of light here is on the left. So light enters in that direction from left to right. In tube 1, without any light scattering etchings shown on the left, there is very little signal enhancement here, judging by the values of these position-dependent enhancement factors alpha z. Tubes 2, 3, and 4 have different patterns of light scattering etchings, and they show much greater enhancement and different light distributions profiles. So for example, tube number 2 is etched only in the bottom half of the sample area, and we see that signal is enhanced in that area, but much less so in non-etched area. But if we add more etchings towards the light source, we can increase both the light intensity there, and we can also affect the shape of the profile, making it more uniform. So here it is still not particularly good, but we've got space to add a few more etchings there, and that would flatten the profile and will make it both high in absolute value and fairly uniform. So by applying specific etching pattern, the NMR torch tubes can be made to illuminate the samples uniformly along the whole length. And we think it will be great if this thing will be done not manually, but using some industrial machining methods for consistency, so that such tubes can be available for community as consumables. So let's look at another example of a photo switch, which can be used as actinometer, able to quantify light inside the NMR sample. Here, the ability to use two LEDs at once is extremely beneficial. Normally, to determine light intensity, one needs to run a known chemical reaction with known quantum yield, repeating it at a different starting concentration. So you need to handle a lot of different samples. With our approach, we propose to use a reversible photoreaction and two LEDs with a single sample, where one wavelength just sets the necessary starting concentration of the compound, and another LED triggers the reaction to be measured. So this molecule, DAE, can exist in open form and in the closed form, and UV illumination at 280 nanometers shifts the equilibrium towards the closed form. And the concentrations of the forms present at any particular moment can be quantified using either proton or fluorine NMR spectra. And here we can easily toggle between UV and visible illumination, visible with green light, while monitoring the kinetics of all these transitions. And then we can determine, and you see with each prolonged UV illumination, we set increasing concentrations of this closed form. And then we can determine the dependence of closed form conversion rate versus starting concentration of the closed form. And knowing the quantum yield of the reaction triggered by green light, we can then derive the real light intensity of green light inside the NMR sample as the number of photons reaching the sample per unit of time and per unit volume. Knowing the total sample surface area which is illuminated, we can estimate photon flux density and the irradiance right around the sample. And by the way, as we can see, this number is fairly large compared to what we get from using the traditional fiber optic based setup or what we have seen in the literature. Let's look at another example of photo switch, amino-azobenzane. So the equilibrium between its trans and cis form isomers is dependent on the illumination wavelength. And by observing characteristic trans and cis signals in the NMR spectra, we can easily determine the concentrations of these forms at any point in time. And then, using 4-colored NMR torch light head, we can toggle between blue, red, blue, green, blue, white, blue, and then light off, observing the evolution of characteristic trans and cis signals in real time, so that we can extract the kinetic parameters for various transitions and determine also photostationary states. Of course, any photo switches can be studied in this way, and different combinations of colors can be used as appropriate. For example, instead of white light, we can use UV light. And finally, we wanted to show an example of very high power UV delivered to an NMR sample, as may be necessary to drive some of the chemical reactions or when measuring photostability of pharmaceuticals. International Council for Harmonization of Technical Requirements for Pharmaceuticals for Human Use, or ICH for short, has Q1B guidelines that describe the light dosage required for photostability testing. To benchmark the dosage, the guidelines suggest to use 2% quinine as actinometric system with prescribed dosage corresponding to a greater than 0.5 increase in light absorbance at 400 nanometers following this UVA exposure. To check if we can meet these guidelines, we use the light head housing 10-watt LED UVA LED with quinine sample, with this 2% quinine sample. So within minutes, we have seen changes in the NMR spectra with some signals appearing and some signals disappearing, which can be then tracked and assigned to different moieties in the molecule. Importantly, the necessary UV dosage is achieved and exceeded in less than 2 hours, demonstrating that in situ photostability testing with online NMR detection is possible. So we see we can achieve more than 2 units increase in optical density at 400 nanometers, and the sample becomes very, very yellow. So we completely degraded it. So as a conclusion, we can say that the new NMR torch setup is universal and flexible. It provides powerful and multi-wavelength illumination. It can be used for a wide range of photochemistry applications. In our experience, it is very convenient to use with great flexibility in terms of wavelength choice. You can stick any LED there. You work with sample tubes as normal. You wash them, fill them, put the cap on. If you want, you can work in the glove box. Then you use NMR torch light head on the top of this whole capped tube. Only the usual sample tube containing the sample is placed in the NMR active volume, so no issues with shimming, solvent suppression, or spectral quality. You can use your favorite nuclei, which best reports on your particular system. The downside, the sample volume for 5mm NMR torch tube is limited to around 170 or 200 microliters. And of course, one can use NMR torch principles with larger NMR tubes, and also other arrangements are also possible which do not sacrifice sample volume at all, and some of these arrangements would work very well with benchtop spectrometers as well. So finally, the acknowledgements. The experiments presented here were mostly done by Dr. Jack Bramham, and we are also grateful to Dr. Matt Cliff for looking after the NMR facility here in Manchester and helping us with experimental setup. The project was funded by the EPSRC, New Horizons, and thank you for your attention, and I will be happy to answer any questions at the end of both presentations.
Brilliant. Thanks very much, Sasha. That was absolutely fascinating, and we've got some really good questions coming in as well. So I think it's time to just thank you again, and it's time to go to the second poll before we have James's presentation. So if Chris can just cue that up. Lovely. So our second poll is, if you were to use light-coupled benchtop NMR capability, how important for you is the ability to do high throughput? Not particularly important. We only run one-off samples. All the way through to high throughput would be essential, and even some automation might be essential as well. So I'll just leave that open for people to vote on for a little while. And just to remind you that you can, even though, as I said, we've got plenty of good questions coming in, you can still submit questions all the way through the rest of the presentations. Just get them in that questions box at the bottom of the GoToWebinar panel, and we'll be able to see them. If you, for any reason, are having any technical difficulties, don't worry. You will get a link to the recording of this webinar in a couple of days' time, and any certificates of attendance that you might need as well. And just while the last few people vote, just obviously this is as part of a series of Chemistry World webinars. If you want to know what else is coming up, then after we've finished this session today, do head over to the Chemistry World website and check out what we've got coming up on the webinars tab. Brilliant. Okay, so I think we're more or less there. There's not many more votes coming in now, so I'll ask Chris to close the poll and just show us the results. Just a fair mix of people. So I think people obviously looking at this for various different kind of reasons. So yeah, that's quite interesting, and I'm sure that'll be very useful to James and the team as well. So now I will hand over to James, ask him to bring on his webcam and make sure that we can hear you. Brilliant. Okay, so I think you're going to tell us a little bit more about Oxford's benchtop instruments and how they can be used in this kind of configuration. So thanks very much. Off you go.
I am indeed. Thank you very much for that, Philip. And it was really interesting to see both how many people were interested in doing photo NMR, but also sort of how important people place automation and high throughput in that. And obviously these are things that often come into discussions when you're looking at both high field and benchtop NMR spectrometers. And I think that addressing some of those differences is probably quite a useful place to start before we start looking at how this photo NMR can be implemented on a benchtop. Now, obviously, all of the work that Sasha showed was done on a high field instrument. Obviously, those require a lot of liquid helium, liquid nitrogen, typically in their own environment, well-controlled facility, usually with a dedicated operator. Now, with benchtop NMR, we're in a very different situation. We shrink that technology down, we put it on the bench in a lab, or in fact, as Sasha also mentioned, potentially even in a glove box. And that means that you don't necessarily require that expert operator to use it, and it's right there next to where you're doing your chemistry. We take the sort of high field approach in that we decouple our magnet and our electronics, meaning that we can always provide the best possible NMR performance while still retaining that small form factor. So in the schematic that we have on this slide, we have the magnet where you place your sample sat on the bench there, and you can place the electronics rack wherever is convenient for you. Now, obviously, there's a number of things that are important for a benchtop system. Now, to be on the bench, you don't want those liquid cryogens. It needs to operate at normal room temperatures. It's obviously a big advantage if you don't need to have a dedicated operator. If you can use it there, it can be used by your synthetic chemists while they're doing their reactions. It's a much more advantage. It also needs to have a minimal stray field, so it's safe to have in that environment. And obviously it needs to be of a form factor that means it can be placed on the bench. Now, once you've got it on the bench, it also needs to be able to perform with a specific specification that allows you to get the results that you need. And typically when we're talking about NMR, we talk in terms of resolution, sensitivity, and stability. And I'll talk about exactly what those look like on our instrument in a couple of slides' time. Just to give an overview of the instrument itself, the X-Pulse that all the data that I'm going to show was collected on. It's a very high resolution benchtop instrument. We have a resolution of better than 0.35 hertz at the full width of the half height of a peak, and at a full width of less than 10 hertz at the height of the carbon satellites. The instrument is very high sensitivity, so better than 120 to 1 for the broadband system that, again, this data was that I will show was collected on. We have pulse field gradients as standard, which means that you can start to do more intricate experiments or speed up your 2D experiments with gradient selective versions, or in fact start to do some diffusion spectroscopy, as well as using things like shaped pulsars to do the solvent suppression techniques that Sasha was also talking about, that can be used much more effectively with the NMR torch than potentially with a fiber optic arrangement. And the instrument itself is a 3-channel spectrometer. So we have a deuterium lock channel, which can provide either an internal or an external lock. We have a proton fluorine channel, and then we have this broadband fully tunable X channel. So you can analyze whatever nucleus is important for your chemistry. And what can also be important is the X-Pulse is the only benchtop instrument with a user removable probe. So when you're thinking about how you want to couple in your light source to your NMR, that can again be very, very important. We have the ability to control these reactions and understand your chemistry over a range of temperatures. We can do this in potentially flow NMR, and we could put that in a situation where you can move it around with its own mobile custom designed workstation. But I talked about what that performance looks like, and we tend to break that down into resolution, sensitivity, and stability. For resolution and sensitivity, there are particularly well-defined measurements for what we would do with NMR. So here, a single scan of acetone, of chloroforming acetone, and you can see here that with a specification of better than 0.35 Hertz half height, here we show 0.26, and at the height of the carbon satellites with the specification of better than 10 Hertz, we see 9 Hertz. And again, that means that when you're looking at potentially crowded spectra, which on a benchtop at benchtop frequencies you invariably get, that can make analysis significantly easier. In terms of sensitivity, we measure the intensity of that methyl quartet in ethyl quartet in ethyl benzene, and we measure the height or the intensity of that strongest peak there with relation to the baseline. And in this case, for that same probe, we get a signal to noise ratio of 130 to 1. So the specification here was 120 to 1. Now with these benchtop instruments, they're based on permanent magnets. Those materials themselves are hugely temperature sensitive. So in order to ensure that you're seeing changes in your chemistry and not just changes in your instrument, you need to be able to control that incredibly well. So we need to measure stability. Now, there's not necessarily a particularly well-defined way of doing this for benchtop NMR, but using something like a methanol NMR thermometer, where we would see temperature changes in the sample, so the separation between those two singlets there as a function of the temperature of the sample itself. If we plot that after acquiring spectra over 3 hours, we find that with our instrument we have a temperature stability of better than 0.002 over that 3-hour period. Now, benchtop NMR in itself has a number of potential advantages versus high field for allowing you to do these photochemical experiments. Now, when you're looking to position a light source, it's much easier to position a light source in the or next to the spectrometer. You can potentially put those power supplies much closer to the instrument. And if you need to potentially adjust positioning during your measurements, then it's much easier to do that because it's right there next to you on the bench where you're doing your experiments. It's not in the middle of a large cryogenically cooled magnet. Now, the X-Pulse itself also has an open bore. That means that there are a number of possible illumination options that actually Sasha showed in his presentation. So with the NMR torch, we can do effectively this top illumination, but the bore's completely open. So with no changes to the probe itself, you could even consider illuminating from the bottom. Now, the design of the magnet in the X-Pulse also means that you could consider in-probe illumination. What we have is we have a flat pole magnet where effectively around the probe itself, you would have this sort of area where you could look to put those LEDs to provide illumination of the sample, all contained within the instrument. So still allowing you to potentially do those things like flow NMR. But today we're talking about how we use the NMR torch with the X-Pulse. And that really is quite simple. We take our NMR torch tube with our specific light head, either this one containing red, green, and blue LEDs or a UV LED. We literally drop it into the top of the instrument and it slides into position. And then we can change which LED we're providing power to give us red light at the sample, blue, green, or any combination of those LEDs present. And that's hugely important, as Sasha said. That allows you to provide all sorts of variations on the experiments that you're doing without having to change the setup itself or how you're or the chemistry you're looking at. Now, just to show a couple of applications, essentially how those examples that Sasha showed translate onto the benchtop. If we start with that 4-aminoazobenzene photo switch, now we know this molecule has a very well characterized photo-induced isomerization, and those two isomers have distinct NMR spectra. If we look at the high field spectra that Sasha showed with relation to the benchtop spectra, we can see that obviously due to the lower field, we get less dispersion in the spectrum. However, we are able to very, very easily see the difference between those two isomers. So the trans isomer on the left here, we see not necessarily as well resolved to the baseline, especially in this group here, but actually we see very clear and distinct peaks. When we go to the cis isomer, we can again see that there are significantly more peaks in the spectrum, clear new peaks arriving, and spectral differences in those other regions. That means that performing those same reactions, those same different frequency illuminations, we can track and monitor that isomerization. That means that we can induce those different population equilibria, and we can track that as a function of both time and illumination frequency. So if we start in our dark state, and then we turn on our blue light, we can see that we drive the population to some equilibrium position. If we then go dark again, we see that that slowly decays back to our initial conditions, but never quite gets, in this case, to that starting point. By illuminating that very quickly with red light, we can drive those two populations back to their initial starting conditions, essentially our dark state. Again, we can illuminate with blue and get back to that same population. We can start to think of things like determining rate constants and those equilibrium points from doing this sort of measurement. If we go to green light, you can see that we actually form ourselves a nice new equilibrium point. If we use both the red and the blue light to give ourselves a purple light, we get a very, very slightly different equilibrium point, but not dissimilar to green. Go with blue again, we get back to our blue population equilibria. Going red, we very quickly reverse back to our initial conditions. And going green, we get back to our green population. And that shows that in real time, you could do this right there as you're doing your chemistry on the bench next to you. There's sufficient dispersion, there's sufficient signal on a benchtop NMR instrument to give you real understanding of the chemistry you're doing right there where you are doing it. And I think that's hugely important when you're trying to understand exactly how these processes happen and what that means for the reactions you're trying to understand. Now, obviously, Sasha also talked about the chemically induced dynamic polarization experiments. And again, if we recreate that same experiment, so 6Fi with FN and using our 3-watt blue illumination, we should be able to see that same behavior. Now, obviously, we're on benchtop. Our sensitivity, being a function of the external field strength, is lower. So first of all, okay, we'll start with 100 times the concentration. So here we're 100 millimolar as opposed to 1 millimolar that Sasha showed. And using our 19F NMR with no illumination, we can see a small peak just above our baseline there. Now, this comes from the fact that although we're at a reasonable benchtop concentration, the sample space is a little smaller due to the using the tube as the light guide. But we thought, actually, let's push this. So we go to our 1 millimolar solution with no illumination. And you can see we can't really see anything. Okay, there might be a slight disturbance in the baseline there, but no one's really drawing any conclusions from that in a single scan, which is what these are. However, you turn on that blue illumination and you can see that we get a significant enhancement, even over 100 times stronger solution. if we overlay those three spectra, you can see that actually what we achieve if we take into account both the enhancement versus the 100 millimolar solution and the enhancement from the light and the dilution of the sample as well, is that on a benchtop where we'd previously seen roughly a 64 times enhancement of the signal in a high field system, we get closer to a 300 times signal enhancement, which is a hugely powerful tool when we know that when you're on a benchtop instrument, sometimes sensitivity can be a limiting factor. And it's not just a one-off. That enhancement of signal can be seen over a long period. The signal decays with time, but what we did here was we took that same sample, we turned the light on, turned the light off, turned the light on, and tracked the decay of that signal with time. We can see that there is obviously a decay as we do this with more illuminations. We effectively bleach our donor dye, but what we actually do see is even once we're bleaching, we're still seeing significant enhancement that really makes this useful as a probe for all sorts of different chemistries on the when you're looking at benchtop NMR. And finally, using that UV light head. One of the beautiful things about benchtop NMR, effectively all this light and all the electronics associated with the illumination and the cooling for any of these LEDs that do get a little warmer, like when you're using a high-powered UV, is that they're all external to the instrument. So there's no effect on the spectrum at all, other than that that's induced by the illumination. You can see here for naproxene, we illuminate the spectrum, or we illuminate the sample, and we can see quite quickly a decay in this signal. Within 10 scans here, we're seeing a significant decrease in that signal. So we're seeing significant degradation of, in this case, naproxene, common API. And you can see once we actually extracted those samples from the instrument that we have quite a different final product to where we started. But again, that means that you can test your drug candidates right there on the bench where you're doing your chemistry, where you're looking for your leads, to understand whether you're going to have these photo degradation issues when you look to combine those into final drug product. So just to conclude, Benchtop NMR is a perfect platform for photochemistry studies due to its form factor. It's easy to access a sample area. We can get much closer proximity between the sample, light source, and its control electronics. And there are a huge range of potential applications for in-situ photochemistry, from photodegradation to photocatalyzed reactions, signal enhancement, and many more. And we would love to hear about all those different ideas that you might have for how you would use in-situ photo NMR. So thank you very much for listening.
Brilliant. Again, thanks, James. Absolutely fascinating presentation. So just before we go into the Q&A session, we have the third of our polls. So I'll just get Chris to cue that up. So the last question is, would you use in-situ sample illumination with any of the following? Would you just use it with benchtop NMR, just high field, or a combination of the two? So I'll just give people a little bit of time to vote through. And reminder, we have had some absolutely fantastic questions coming in. Thank you all very much. It's definitely not going to be possible to get through all of them in the time that we've got. But James and Sasha have both said that if there's any questions that we don't get through, then they're happy to kind of correspond with people by email after the main session is finished. So I'll just leave it a little while longer for a few more of you to vote. And as I say, there is still time to get some questions in. If we can still bump you up the list if you put a good question in, so don't worry about that. And like, as I say, there is, if we don't get through them, James and Sasha will be available to do them afterwards. So don't be afraid to put more questions in if you've got them. Okay, I think we're more or less there. There's not very many people more voting now. So we'll see the results. And yeah, again, a bit of a mix. I mean, I guess that probably reflects the kind of audience that we've got through. James, do you want to say anything about that? If we can just show, we can close those results now, I think.
Well, I think it's very nice to see that people obviously are interested in using this with Benchtop NMR as well as high field. I think it's obvious that people want some corroboration of their data across the two different, quite different techniques, really, although they're complementary and they use the same sort of physics to generate your signal. The data you get is actually quite different in many ways. But it's really nice to see that people want to use this technique, and actually the fact that there's more people that maybe want to use it on the benchtop rather than just on a high field.
Great. Okay. Well, thanks very much, James. I think we've got Sasha back with us again. It's time for the live question and answer. So as I said, we've got some really fantastic questions. So I'll kick straight on, and I'll ask you guys to be relatively concise with your answers if you can, because we've got quite a few to get through. So first question, there's a few questions about the kind of technical side of how the NMR torch works. So we'll blast through those pretty quickly. Sasha, we've got a question from Mark. Does lowering an electrical cable into the NMR machine produce any kind of interference? Can you tell us a little bit about that?
The short answer is no.
Okay. It's the kind of thing, you sort of think, oh, electric cable in a big magnet.
Well, there are lots of cables around NMR spectrometers.
Yeah. Fair enough. Great. Okay. And probably Sasha again, maybe James coming in for this one. We've got lots of people, Peter and several others, asking for more information about the NMR torch tubes, things like what the wall thickness is, what they're made out of, and again, lots of people asking where they can get them from, both the tubes and the transparent caps that you mentioned, and are they available in different sizes as well? So maybe, Sasha, do you want to go first on that?
Yeah. So as a prototype, we used standard heavy-walled NMR tubes that are available commercially, but obviously they do not have scattering centers, so these have to be introduced, and we have done it in-house manually. The same principle can be used for any other tubes of larger diameter as well, so it is possible to do it. Now, quartz versus standard glass. We tried both. If you go to UV, then of course you would want to use quartz glass, and then you get much higher light intensity there. Although we did try standard glass, and we still can degrade with UV the NMR samples. It's just degradation is a little bit slower, but even standard glass works. There was a question, how low can we go with UV? So I've showed you examples of transition triggered by 280 nanometers. That was the shortest LED that we tried. What was the other question? Where do we get them? So I think the best scenario would be if these tubes will be produced commercially by somebody and sold as consumables. But I guess if there is enough interest in the community, that can be maybe arranged, hopefully. I would be more happy to buy them somewhere than to make them myself.
But at the moment, if people wanted to try this kind of thing, the best thing to do is maybe to get in touch with you and work out how to do it themselves.
Yeah. There will be some publications coming.
Perfect. And you mentioned obviously need transparent caps for the NMR, which are not necessarily standard.
So again, these are not commercially available. We tried a lot of makeshift caps of different construction. Again, hopefully this will be described in the paper that is about to be, I hope, sooner or later it will be published. But any cap that you can kind of create in your lab that is transparent enough would do.
Brilliant.
And just to drop in there, Philip, there's a question about whether you can use this with potentially larger sample size time domain instruments. And I think that generally the principle is yes, you can. We haven't done that as yet. Sasha hasn't done that as yet because he's focused on spectroscopy, but you can understand that with that larger sample size, you may struggle in sometimes to get the light right into the center of that sample, but actually, there's things you can do to mitigate that. And also, some of the things that might open up in terms of the type of materials that you can look at, the type of things you can understand with illumination and time domain NMR, things like potentially changes of cross-link density in polymers with UV illumination is kind of an exciting area to look at as well.
Brilliant. I think that's a really nice, thorough answer to all of those questions. So thanks very much, guys, both of you. Okay, so the next, I've got a couple of questions around sort of the kinds of experiments you can do. So we have a question from Eldrick, which is around what kinds of molecules do or don't work very well with their photo-induced CIDNP. Maybe I'll get Sasha to come in on that one first, but James, you might have something to add.
So I'm not sure there is a general answer to this question. Sometimes it works, sometimes not. It depends really on concentrations, on dyes, on how well the dye matches this particular molecule, how they interact. So yeah, it is very deep science there, or maybe even dark art rather.
Okay.
But
yeah.
importantly, our method enables to explore that quite efficiently and very quickly.
Right. So it's a case of building up case by case, working what works best with your own particular system, I guess.
Yes, exactly.
Right. Okay. And maybe James can come in on it. So we had a question from Andrea around solid state NMR with this kind of in situ elimination. Would that be compatible with the kind of systems that you're looking at?
So the Benchtop NMR spectrometers are predominantly or pretty much exclusively solution state. I'm trying to think how you would try and couple this into a solid state system if you were looking to have to look at a magic angle spinning system. That becomes very complicated because you've got things rotating quite quickly, and but then again, as I previously said in the answer, depending on what you're exactly looking at, what sort of information you're trying to probe, other techniques that allow you to look at solids, such as time domain NMR, some solids could well be very useful, or provide you with at least some of that information that you're looking at from your solid samples.
Yeah, maybe we'll leave that as a challenge to someone in the audience to work on and develop something of their own. Maybe they can get in touch with you. Okay, so I guess the next one is again for James. You mentioned very briefly at the start that the Oxford Instruments setup can be used for flow NMR. I've got a question from Emily. How would you change the setup to make it work for flow?
So we have some ideas as to exactly how we would do that. With the X-Pulse, we have essentially a bespoke custom designed flow cell as it is. It's not out of the realms of possibility given the design that we already have of that and the way that the NMR torch works, to couple those two together quite nicely. So I can definitely see how that would work in a flow environment. I think it would actually work quite nicely, especially if you're looking to catalyze reactions, etc. I think the questions that always get asked at that point are whether it's better to illuminate in the instrument or whether it's better to illuminate your reaction vessel and probe the results of that. But actually, those two things are probably really rather complementary.
Brilliant. Okay. We're probably down to the last question now because I think we're very close to time. So I'm just going to ask a question from Jeffrey, and I guess maybe this will go to Sasha first. He's asking a question about studying more complex systems like UV photopolymerization. What's the sort of level of complexity you can start to look at, and what's the limiting factor, I guess, in this kind of setup?
So NMR itself is a very universal method, as we all know. If you can see something with NMR, essentially with NMR torch, you can see this same something, but in the presence of light. So if something happens upon illumination, you essentially can see the changes in the NMR spectra. So with polymerization, presumably you'll be changing relaxation times, or spectrum will be broadening, or something will be shifting. So yes, we can use UV illumination. I've shown an example where we used 365 nanometers, where we used 280 nanometers. And it basically, yes, you can deliver this light easily, or you can deliver both 365 and 280 at the same time, or toggle between them. So in our experience, up to 4 LEDs of different colors is straightforward.
Brilliant. Okay, well, thank you very much, guys. And as I say, there's several more questions that we haven't managed to get through, but they will all come to you, and you can try and answer some of those offline. So all that remains, I think, is for me to thank both James and Sasha for some fantastic presentations and some really good answers to some top quality questions from our audience. So well done, everybody, all around. Thanks again to Oxford Instruments for sponsoring this webinar. Thanks to the audience for attending. It's you guys that make these things happen and make them the quality that they are. So thanks very much. You will, as I said earlier, get an email in the next couple of days with a link to the recording and a certificate of attendance. And if you liked this webinar, then do check out chemistryworld.com/webinars to see all the other topics that we've got coming up in the next few months. And I hope to see you in another webinar soon. I'm Philip Broadwith, Chemistry World's business editor. Thanks very much.